Welcome to our talk and paper HyperPosePDF, predicting the probability distribution on SO3. I am Timon Höfer, and I'm happy to present our work. Traditional signal representations are discrete. For example, in the case of an image, a discrete set of pixels with RGB values represents the image. A continuous representation would be through a function that is defined on the pixel values and maps into their respective RGB value. Simply writing down such a function is analytically not tractable. Implicit neural representations use multilayer perceptrons to represent signals such as images, sounds, occupancy, radiance fields, and more. They represent them by mapping the input coordinate of a signal to its value. For example, here we have a multilayer perceptron that takes in the XY coordinates of an image and outputs the RGB value at the corresponding location. They have multiple advantages, such as being resolution-free, differentiable, and simply giving better performance when used in many tasks. Instead of directly using the coordinates as input, it is standard to first apply a Fourier encoding to the input. A standard encoding is, for example, the positional encoding, which uses log linear space frequencies for each dimension. It has been shown that an initial Fourier embedding given by gamma is crucial for the performance. Here we can see a comparison of results for the image regression task and the 3D shape regression, where 3D coordinates are mapped to 0 or 1, depending on whether the point is part of the object or not. In our work, we want to see whether it is possible to use an implicit neural representation on SO3. Specifically, we want the MLP to represent a probability distribution on the rotation manifold that maps a rotation to the probability of being the underlying rotation. Our architecture is as follows. We use a vision network, for example, a ResNet backbone, that takes an image as input and outputs the weights for another network. This means it acts as a hypernetwork. The network for which we predict the weights is the implicit neural representation that maps a discrete subset of SO3 to the individual probabilities of being the underlying rotation of the object present in the image. We utilize a newly developed strategy to visualize 3D poses introduced by Murphy and others. As any rotation can be represented by 3 illegible elements, one can use a 2-dimensional sphere, and the third dimension is represented by the color. Hence, we can now look at qualitative results of a cylinder with a red marking. Note that whenever the red marker is visible, the rotation is unique. Elements of SO3 with a positive probability are visualized as points on the grid. Therefore, the filled area depicts the predicted pose, whereas the circle indicates the ground truth pose. In case of the red marker being on the back, we can see that we predict a continuous symmetry, contrary to a cylinder that is not marked. The symmetry line has a gap in between, which reflects the subset of rotation with the marker being visible. We evaluated our method in the log likelihood and spread metric. We can see that we get superior results in the SimSol1 dataset, consisting of symmetric objects like the cylinder or tetrahedron without markers. In the SimSol2 dataset, consisting of similar objects with markers, we still get better results. Note that no symmetry annotations have been present in the SimSol2 dataset. Therefore, we could not measure the performance in the spread metric. To check whether our approach is also applicable in the task of single pose estimation, we tested it on the Pascal 3D Plus dataset, which is a subset of the Pascal VOC dataset with additional pose annotations. Here, we could achieve comparable results like other methods. I want to thank you for listening.